Well, thank you, Linda, being so kind to introduce me and really not speaking about my age, saying that I'm only a long-term expert. It's really a great pleasure to be here and to spend a few days with Linda's group. So if the time after my, as usual, hopefully not too long talk, if there's any question that cannot be answered directly after the talk, I would be happy to see you in during this week. So before I think I will go into the talk, I have to explain to most of you where Giessen is. And so this is the landscape of Europe. There is Germany more or less in the middle of Europe. And if you have the German map, where of course one of the fixed points is Frankfurt, where you usually fly in. So just about 60 kilometers north of Frankfurt, still in the metropolitan region of Frankfurt, Giessen is. And the university is more than 400 years old. And Giessen is, in fact, that's an unknown fact. You will know lots of university towns in Germany, but maybe not Giessen. In fact, it's the town with the highest density of students. We have 85,000 population, and in that we have 38,000 students. So it's really a true academic town. And if you forget that, some of you may publish in journals of the ACS. And if you do that, you should know the logo of the ACS. Have you ever asked yourself what is the meaning of that logo? Any idea about, let's say, the upper part? This is a quite old logo and still the active logo of the ACS. So what is the upper part telling us? Usually chemistry is composed in the old sense of two parts, right? Analyzing things and making things. Now this is phoenix rising out of the ashes. So this is a symbol for making things out of fire, something a chemist is doing. Now what is the bottom part? If this is synthesis, this has to be analytics, right? And this is in fact the symbol for the so-called 5-ball apparatus, which was part of the quite new elementary analysis Justus Liebig, in fact, invented at Giessen. So he worked for 30 years in Giessen, and his original lab is there. And as he has had many students, and the second president of the ACS was at Giessen at his time, from 48 to 49 in the 19th century, and he thought this is a good idea to take this part of an analytical device to put it into the logo of the ACS. So whenever you publish in an ACS journal, you see the logo, you should remember my university, because it's most people in America don't know that. Okay, so let's come to the real part, and I think I will, as I think some of you are really experts, so for those, maybe it's maybe the talk may be a bit too flat, but some of you will not be so deep into solid state electrolytes and solid state batteries. So I have an extended introduction, and I have to speak about conductivity in the solid state, ionic conductivity, of lithium, of course, a focus to. Then a bit more about stability, and at the end about fuel cells, a bit about mechanics and some issues of that. One of the, I think, key messages is for those who are, I think, very familiar with lithium-ion batteries, and if you would speak to specialists on lithium-ion batteries, ask them about solid electrolytes, they would say that solid electrolytes are poor conductors, but very stable. Now, poor conductors, this is just, I would say, one of the misconceptions, as you will see. They can be quite excellent solid electrolytes, as also Linda and her group are showing regularly. But they're not so stable as one could suspect, because people think often that solid electrolytes are stones, that they should be stable. Now, thermodynamics will tell us quite a different story, at least for the best conducting electrolytes. So let me start with a few prerequisites into solid state batteries, which is, so to say, the background of well, ultimate energy density, power density, and safety in the battery world. And what you see here is a picture. This is a slightly modified, colored SEM picture of a typical industrial cathode material. This is a nickel cobalt manganese oxide in a thiophosphate solid electrolyte matrix, where you already see one of the issues is, of course, contacts between two solids. And that will be part of the talk at the end. Now, status quo of batteries today is, of course, that the state-of-the-art technology is lithium-ion batteries. And we'll have a slide on that. Now, the problem is that these lithium-ion batteries already work quite well. Definitely very well, and we use them. Millions, and maybe hundreds of millions are being used. The problem is during the last 26 years, since the, let's say, first commercialization by Sony, the energy density of cells. So this is the gravimetric, the red, and the blue is the volumetric energy density. And this physical chemical limit is an estimate of the volumetric energy limit of lithium-ion batteries. Because already today, there is, I would say, by engineering, proper engineering, and we have come quite, I would say, closer to this limit, which of course at the end would be the limit of having maybe only the active materials in a cell and only really the physically allowed final limit of passive materials, like a very thin electrolyte layer and so on. So definitely the lithium-ion battery will have a physical-chemical limit. And I think engineers come closer and closer to that as long as there is no, I would say, revolutionary material coming up. And well, I think chemistry is not that much about revolutions. If you know our landscape is the periodic table of elements. There's not so many, I would say, surprises to be expected there. So anyhow, there's the hope that we can go on if we can employ the lithium metal anode, which is not done today. So there's internationally lots of activities in academia and in industry in trying to look for solid-state batteries, where essentially we do not work anymore with a liquid electrolyte, and then may at the end use lithium metal anode. The problem is there is still a number of challenges. So which electrolyte really will be used at the end? So that's not quite clear. Can the lithium metal anode be used? So that's also not quite clear. So there's still quite a number of open questions. Anyhow, I think despite the fact that it looks as if solid-state batteries are something quite new and recent, in fact, solid-state batteries are already were used in the 1960s, the silver electrochemistry. So silver rubidium iodide, to those who know the textbook, you will find that silver iodide and its variant, the silver rubidium iodide, has really an extremely high conductivity of 0.3 Siemens per centimeter. This is still not matched by any lithium-ion conductor. So this is one of the best solid electrolytes. And at that time, there were kind of button cells for medical purpose being constructed. And just as a side comment, one of the key issues today is the question whether one can have very fast metal electrodes at a solid electrolyte. And we did some work in the 2000s with silver electrodes on silver solid electrolytes. And at that time, we already found that it's possible to have electrodes which have very, very high exchange current densities in the order of 0.1 amp per square centimeter without any without any, would say, serious overvoltage. So there's no physical reason why there should not be high-rate metal anodes. So this is just a comment, I think, which I will work out a bit later. I think the hype for solid-state batteries essentially started with work by Professor Kano from the Tokyo Institute of Technology and Toyota, where he showed that this Li10 GeP2S12 LGPS phase is very, very high and had at that time the highest conductivity of any lithium solid electrolyte of 12 millisiemens per centimeter. For those not familiar with batteries, I think a typical liquid electrolyte you would use today in a battery has a conductivity of about, total conductivity of about, let's say, 8 millisiemens per centimeter. Only half of that, roughly, or less than half of this lithium-ion conductivity, because the anion also takes part in the conductivity. So this is better with respect to the lithium conductivity than liquid electrolytes we use today in lithium-ion batteries. So that created quite some severe interest in the solid electrolytes and solid-state batteries. They already showed that was 2011, they already showed a kind of button-type cell, which operated quite nicely. And since that time, Toyota is somehow still, I would say, driving the field. And today, we're in a period where I would say 2016 on, where already, I would say, kind of road-to-road process solid-state batteries are being investigated and developed. Still, there is no, I would say, commercial production of these solid-state batteries on lithium basis, but there is a very high pressure, I would say, to go that way. I think there's an interesting parallel development on the oxide side of lithium-ion conductors. In 2007, Werner Weppner and Venkat Tangadurai, who is now, I think, back in Canada, in Calgary, they published this garnet-type lithium solid electrolyte, which is nicknamed as LLZO. And, well, this has, I would say, an order of magnitude lower conductivity in the maximum case, but this is another, I would say, line of solid-state battery development. Most, I think, companies today work on the sulfide-based electrolytes because they have this very high conductivity, but there is other groups and startups working on these oxides, despite the fact that, of course, these are real ceramics with all the disadvantages of real ceramics. Okay, so I think all of you, know how in principle a lithium-ion battery works. Traditionally, we have the graphite anode, and we have a layered oxide cathode and a liquid electrolyte. And of course, this cartoon always is in a certain sense misleading because in a true cartoon, which is more realistic, the electrolyte gap with the separator should be extremely thin. So today, I would say typically the electrodes are thick in the order of 100 micron, or even a bit more, and the separator is only 10 microns and even thinner today. And for example, the separator becomes thinner and thinner because you gain, of course, energy density if you reduce the thickness of your separator. That may lead anyhow to problems with short circuits, as Samsung experienced with the Note 7, where they somehow, I think, went a bit beyond the technical limit and ran into problems with short circuits. Now, we replace the liquid electrolyte by a solid electrolyte. Again, this cartoon will be a bit misleading because the electrodes are porous, and the electrolyte also is in the electrodes. The question is, what do we gain? So I think the often main issue is that batteries should be safer if you use solid electrolytes. In fact, today, nobody ever has really proven the higher safety of large-scale solid-state batteries. So this is an unproven, I would say, hope yet. Energy density will only be higher if we can employ really the lithium metal anode, because if you just replace the liquid electrolyte by a solid electrolyte for an existing lithium-ion battery concept, you will not gain energy density, you will lose, because the solid electrolytes have a higher density. So you can only gain if you employ lithium metal anode. And rate capability is also an open point. If we employ the lithium metal anode, so far lithium metal anodes always have rather low, I would say, maximum limiting current density. So this is also something which has to be proven. But there is also hope that this may be an advantage, because the solid electrolytes, at least the inorganic solid electrolytes, are single ion conductors. The anion is not moving, of course. So you're forming the energy landscape for the moving cation. So that's a rigid anion lattice, and only the cation is moving. And that means there is no concentration polarization with these electrolytes, as it is with lithium liquid electrolytes. This is definitely an advantage. It may be that you end up then with space charge effects. There is some suspicion that this might be a problem, but this is unproven, I would say, today. At the end, there is also one other advantage. There's simply the construction. You can use bipolar electrodes, and the cell, or let's say battery design, could profit from the fact that you use solid electrolyte that do not, let's say, flow around the electrodes. Anyhow, so key conclusion at this point, let's say, of the introduction is only the lithium metal anode really will bring advantage in energy density. So, and of course, I think the OEMs and the companies don't like to go back. If you have achieved something, you never like to go back to lower numbers. Kinetics may be an advantage, but maybe not with the lithium metal anode, unproven. And what is, of course, clear, you need to go to an efficient processing, and probably you have to change the processing technology for solid-state batteries. On the other hand, we already see that startups and companies try to employ the same technologies that are being used for lithium-ion batteries. So at the end, it may not be so disruptive as it was expected. So anyhow, I'm not an engineer, so I think this is not my piece of cake. So let's now. I think we have 3 chapters ahead of us, and the first will be electrolyte, then let's go to interfaces, and let's go to full cells. So this is, so to say, the brief outline. Now, solid electrolyte, that will be rather short, because I'm not a synthetic chemist, so I'm always rely on working together with people that make nice materials. I'm more on destroying them and investigating them. So that's why I'm here, because Linda is making nice materials. Well, Linda and her team. So for those who are not so familiar with the electrolyte world, the solid electrolyte world, there's essentially 3 groups, and you may distinguish this, let's say, thin film electrolyte class of materials, where lipon, and you may, as a real chemist, you may suffer a bit from the fact that the abbreviations are, of course, not molecular formulas. So lipon, don't take it as a molecular formula. It's simply a nickname. So essentially, it's a nitride of lithium phosphate glass. where you introduce some nitrogen, and by adding nitrogen into lithium phosphate amorphous material, you get a thin film. You can prepare by sputtering nice thin films, very, I would say, well reproducibly. And this is the basis of microbattery fabrication today, where the LiPo anyhow has a rather low conductivity of a microsiemens per centimeter. Well, this is 3 orders of magnitude lower than, I think, the best solid electrolytes we have today. Anyhow, that doesn't make any problem if you make it as a thin film, 1 micron thick. The resistance is not that high, and you don't lose, I would say, energy in the solid electrolyte film. But this is, I think, so far only used in microbatteries. The problem is if you like to have thick electrodes where 25%, let's say, of pores need to be filled with the electrolyte to really lead the ions into the, let's say, to the active masses, then simple calculus show that you need really very high conductivity materials. So this material only would, I think, ever used only as a separator electrolyte, but not in an electrode. So the other classes, of course, are the polymers, I think introduced into the field by Michel Armand, where I think still PEO, polyethylene oxide, is a kind of standard material. You dissolve a salt into it, and it's something in principle like a polymerized organic electrolyte. And the conductivity so far, I think with different materials you can go up, meanwhile, up to 10 to the minus 4, maybe Siemens per centimeter, but still conductivity is too low, and that's why all polymer-based batteries, large-scale batteries, operate at higher temperature, let's say around 80 degrees C. And this is definitely, I think, at least the companies I have spoken to, I think, seems not to be a concept for practice to really operate heated batteries in a car as a mass product. I think so. That's why I think people are still quite suspicious about the development of polymers. And the oxides, as I said, up to 1 millisiemens per centimeter is the garnets or some perovskites or these Nasekon type phosphates. And as I said, the highest conductivity is provided by thiophosphate. And the 711 glass ceramics is a very prominent phase, a metastable phase, and which has also very, very high conductivity. The advantage of these materials is that they are relatively soft, and the processing is quite easy. The disadvantage is, well, you will have a stinky lab, and need to take some care as easily hydrogen sulfide will form, which is toxic, which is also one of the worries of companies later working with these materials, that you have to avoid, of course, that toxic gases form. So this is, I would say, one of the issues with that material. Anyhow, I think currently, I would say most of the companies focus to these thiophosphates or modifications of thiophosphates because they really provide the high conductivity. And this is just, again, some advantage and disadvantage. The oxides, in fact, are quite stable against oxidation. They are, of course, ion selective. They are very low electronic conductors, but they have a lot of other disadvantages. The thiophosphates, these advantages, so they also have a very low electronic conductivity, very high ionic conductivity, of course, also ion selective. And I think with the polymers, processing is the biggest advantage. If you could make a polymer that has high enough conductivity of room temperature, of course, I think you will be a winner. So anyhow, I think I often make a joke with my polymer colleagues saying that, you see, you had 40 years time to improve the conductivity of polymers, and you didn't do it. Inorganic chemists like Linder and others had, within the last 10 years, improved the conductivity of inorganic solid electrolytes by more than an order of magnitude. So I think simply, as always, the best predictor for the future is the past. I think we would expect even more, I would say, progress with the inorganic materials rather than with polymers. Okay, so and this is again summarizing the world of these solid electrolytes in a kind of a Arrhenius diagram, where the sulfides, of course, are up here at room temperature. This is just the rough, let's say, table of what can be made. So sulfides, phosphates, oxides. Phosphates still a bit better than the oxides. And if you ask what is the highest ionic conductivity you could achieve, and you go back, of course, to simple concept describing ion motion, let's say in a crystalline state, where if everything is very symmetric, only a few jumps represent, of course, your mobility of ions. You make transition state theory. You end up with the fact that the conductivity is, of course, a product of essentially a Boltzmann factor describing the thermally activated jumps and the probability to jump over a hill. And the activation energy is an important factor here. A concentration of charge carriers. Now let's assume that all ions in a sublattice are mobile to make a maximum estimate. And the attempt frequency is in here, jump distance, and some factors that are the same for any material. And you end up with the prefactor to be in the order of, let's say, between 100 and 1,000 Siemens per centimeter, and the Boltzmann factor. Now, if you like to see something like better than 10 millisiemens per centimeter, well, your activation energy need to be below 0.3 eV. And this is, in fact, what we see today. All the room temperature solid electrolytes have activation energies below about 0.3 eV. So this is the design rule. And in fact, in the past, people, if they also look for, let's say, theoretical studies, mostly concentrated just on the activation energy. And this is something which can easily be calculated in theory, in a static calculation. But if you look deeper into that, and this is something Wolfgang Seyer, who's an assistant professor in Giessen, and we do quite a lot of nice work together, showed that if you go deeper into the transition state theory, you will see, well, your activation landscape is of course formed, well, in a very simple picture by overlapping energy parabola of harmonic oscillators. And well, the closer they come, the lower is the activation barrier. But if you make a lattice soft, for example, going from oxides to sulfides, now this parabola becomes more flat. That means, of course, if you look into the equations of the results, the quantum chemical results for harmonic oscillators, that also the attempt frequency, so say the ground state and all the other states will go down. So that means if you go to softer lattices, your activation energy will be lowered, of course, but also your attempt frequency will be lowered. And in fact, if you look deeper, there is a relation between the attempt frequency and the activation energy. It's not independent. So just focusing to lowering the activation energy is only one part of solving the problem of getting optimized conductors. You need to take care of the prefactor too. So, and this is, at the end, you have to find an optimum, and Wolfgang very nicely showed that this can be investigated very nicely by looking for the speed of sound and the speed of wave propagation in solids that is very highly correlated with the ionic conductivity of ions in these materials. So this is just a side comment, and I would think this is a very interesting field of research currently, where of course Linda is deeply involved, which is not so much, I think, my key experience. Now let me just show you that one of the, as I said, the most interesting classes of electrolytes is the thiophosphates, which are found in this ternary phase diagram, this tie line between lithium sulfide and P2S5. So if you mix them, you will end up with quite a number of phases. And as I'm not a structural chemist and a synthetic chemist, let me just summarize it saying that we found out together with Wolfgang, and I think that was very much also motivated by work of Linda. And Christian Dietrich, who just finished his PhD thesis, showed that in principle, the structure of all these lithium thiophosphates can be always somehow traced back to the existence of course, building units, anions, that are, in the simplest case, of course, orthophosphate, just PS4 3- tetrahedra. Now, if you let them condense, you may end up, so here's the orthothiophospate, you may end up, in fact, with the P2S74- ion, which is just corner sharing. You may have edge shared, you may have even phosphorus-phosphorus bonds. And the point is simply, the more you condense your building units, the lower gets the conductivity. Because I think simply these building units have less flexibility and can less help the ions to jump through. So in a very simple, I would say, picture of a chemist. And we already in a very early work together with Linda looked also for this metastable compound, and what Christian did was really finding out what are the best synthesis conditions as, let's say, by thermal synthesis conditions, in fact, to get these different phases. And it's in fact quite complicated. Anyhow, what is the result is if you go too high with the temperature, always you will end up with some condensation, and you end up with low conducting phases. And this made us, well, always you should do something good out of your bad. So I think that means you have to very precisely control your temperature. At the end, we wrote a patent for a protecting separator saying that this is well conducting in a certain temperature window, and if the cell gets too high, well, you end up in this region where the cell electrolyte simply transforms into poor conducting phases and it shuts down. So I'm not sure whether this will be used, but I think at least we had a nice idea. So at the end, this leads to the conclusion that for all these crystalline materials, one of the problems, and this is quite different, of course, from liquid electrolytes. If you take a liquid electrolyte, a liter, you have it here, and to pour it into some different container, the conductivity will always be the same. There is no boundaries in a liquid. But in a solid state, in the crystalline solid state, we have grain boundaries. You will never have a single crystalline electrolyte in a battery. And these grain boundaries have different transport properties, and often, at least for the well-conducting materials, grain boundaries usually are an additional resistance, are poor conducting. And they add up to the resistance. So the garnets, for example, depending on the preparation, can have quite a variation of the conductivity, even if the composition is quite the same. This is the same for the 711 glass ceramics. So you see, this is just the conductivity, Arrhenius curves, of the same composition, just differently prepared. There's a lot of, I would say, variation. So preparation and processing will be really decisive for these different materials. And that distinguishes these materials, of course, from liquid electrolytes. And it's then a question, of course, whether you can manage that during processing and making batteries to get really during operation with the real battery, these high conducting phases, which you obtain in a lab under idealized conditions. Okay, so I think anyhow, ionic conductivity of inorganic solid materials will probably not be limiting. We have excellent conductors. We simply need to employ them to bring them into the cell. So the critical influence of microstructure, I think, is decisive in processing. Okay, let us go to the electrodes. And let's say, okay, the electrolyte side is done. Well, it's not quite done, so there's, of course, always still the need for better materials, but in principle, we have some quite decent materials. Let's go for electrodes, and this is, of course, one of the most critical points in solid-state batteries. And let's start with the anode. Now, if you really like to deal with a lithium anode, you should remember your chemistry undergraduate course where you learned that lithium is the strongest reducing agent we have. And in fact, lithium will reduce everything it comes in contact with, and it means also solid electrolytes. So what we have shown here, that is from the work of Sebastian Wenzel, other PhD student, that you can distinguish three cases, I would say, of interfaces between, let's say, these gray lithium metal here and the solid electrolyte. Now, in the ideal case, you would have a stable solid electrolyte that does not react with lithium. And today, only a single, I would say, well-conducting electrolyte is known that is stable versus lithium. That is this lithium lanthanum zirconate, the lithium garnet, thermodynamically stable. Don't mix that up with kinetic stability. So this means thermodynamic stability. So you put that together, and the garnet will not change. Now, all other materials react. But if they react, there can be two limiting cases. One is, in fact, that the material fully reacts because the reaction product which separates the metal and the electrolyte is mixed conducting, is electron and ion conducting. If this is the case, your cell electrolyte will simply reduce fully and it acts more like an electrode than an electrolyte. Or you get an interphase here which is ion conducting but not electron conducting. And that is the case of the well-known solid electrolyte interphase in liquid electrolytes, where you form an ion conducting phase that has no electronic conductivity and protects the electrolyte from further attack by the electrolyte. And fortunately, some of the good conducting materials seem to show such a nice, I would say, kinetic stability versus lithium. You form a thin interface that is stable. Now, if you look into all existing or investigated electrolytes, in fact, the thiophosphates have really a very narrow thermodynamic stability window. They are really even less stable than typical liquid electrolytes. So they don't behave like the expected stones. In fact, of course, the sulfur is easily being oxidized, and the phosphorus is easily reduced. And that is, of course, why you have such a small thermodynamic range of stability. And interfaces are really a crucial part of these batteries. Of course, lithium fluoride, of course, is extremely stable. This is a thermodynamic, I would say, triviality, that the binaries, of course, are all stable versus lithium. And you see, this is the voltage scale. Only the garnet material here seems really to be stable thermodynamically versus lithium. All the other materials are going to be reduced. Titanium and germanium are easily reduced, even silicon by lithium. Okay, and we essentially, some of my students created a nice experiment in our XPS machine where we take solid electrolytes and with the sputter gun can deposit lithium or sodium on top of the solid electrolyte. and then can intermittently use the XPS detector to see what happens, whether the lithium really reacts with the solid electrolyte. And this is something we do to monitor really the stability of these solid electrolytes. And in principle, we found that, of course, all electrolytes in principle react and decompose. For example, the lipon completely decomposes into lithium phosphide, oxide, and nitride, which is good because lithium phosphide and nitride are ion conducting phases. And at the end, the SEI is better conducting than the original electrolyte. That's why usually you don't see this interface in impedance spectra. And this was quite unknown until a group of Abraham Jägermann reported that first. Now, the thiophosphates all decompose into lithium phosphide, oxide, and sulfide. And here, only lithium phosphide is an ion-conducting phase. So that's why these interfaces are somehow add resistance to your cells once you have the reaction with lithium. Well, and of course, the polymers also, some of them react. Just to show that, in fact, the lithium garnet is stable. So this is XPS spectra, where what we do is we have the garnet material. And before we have, so to say, put lithium on top, you see the spectra as you would expect for lanthanum, zirconium 4+, lanthanum 3+, lithium. And once you deposit lithium, the only thing you will see is some damping of the spectral lines, but no change of the spectral lines. So, in fact, lithium is formed, and we will lose, so to say, the signal from the electrolyte because it's simply covered by the metal film. And we see at the end really also the metal itself. In fact, this is really stable. And the final point on that, which I think from a physical chemical point of view, of course, is nice. So physical chemists usually, I think, annoy their students by always asking for quantitative, for things, for numbers and equations. So the SEI formation on lithium in a solid electrolyte, if a well-covering layer is in fact being formed, the layer can only grow by diffusion of lithium ions and electrons through the layer, by, so say, coupled diffusion. And this is well described by existing theories for diffusion-driven reactions. And if you write that down, you see that you end up for diffusion-controlled reactions always with a parabolic rate law. Because your layer gets thicker and thicker, of course, your diffusion rate gets less and less, so the rate is, so to say, slowed down. And that leads to a parabolic or square root of time law. And if you plot all the resistance changes due to the interface formation at the anode for different materials, so this is the LGPS, this is the 711 phase, this is chloride, agurodite. You see, if you plot the resistance of the interface as a function of square root of time, you end up always with linear relationships. So it's, I think we could prove that, in fact, most of the electrolytes show diffusion-controlled growth of an interface. And, well, for these materials, the increase of the resistance is not too high. This is just some, let's say, 10 ohms per centimeter, which is not too bad. So, in fact, solid electrolytes somehow behave like liquid electrolytes. They also react with lithium. They form an SEI in a solid electrolyte, which sounds a bit absurd, but it's what we observe. So most solid electrolytes form an SEI on lithium metal. So we have to see whether really we have kinetic stability or not. And of course, this is only critical if the formed film has, in fact, a high resistance. So this is all. And of course, if it would have too high resistance for a material you like to use, then you have to modify your surface somehow. You have to find a proper interface or modification as we do it today in lithium-ion batteries. Now, final point for the electrodes is, let's look to the cathode. And if we deal with these thiophosphates, let's take the Li3PS4 as a model type compound. The conductivity is not so superior, but it's a good model type compound. And this is the phase also BASF company proposed to work with in our network. So we looked at that. And what Raimund Curver did, he looked with XPS to the solid electrolyte close to the current collector at the cathode. And he polarized to different upper cutoff voltages from 4 to 5 volt. And what you see is, this is already, I would say, the analyzed result from XPS, that the, if you go to higher cathodic voltages, so to more oxidizing conditions, in fact, we see more and more oxidized species here. Even we see sulfur. So sulfur is even produced here. So what happens is, in fact, that if we have a cathode material here, either current collector or really an oxide, which is used as a storage phase, And if we charge and go to high potentials, in fact, these nice tetrahedra, which I think lead to a nice energy landscape for the motion of the ions, they simply polymerize by oxidation. And if they polymerize by oxidation, the conductivity drops down and your cathode becomes worse. You have a higher overvoltage and your system starts again to fade. So, and that's why, of course, and you remember from the thermodynamic stability range, the stability of the thiophosphates was only up to, I think, 2 point something volt. Definitely too low for the use with oxide materials. That's why today, if you look into literature, these thiophosphates will only be used in practice if you protect them by a coating of the cathode materials from oxidation. So that means if we really like to use these thiophosphates in a solid-state battery, with a lithium metal anode on one side and with a reasonable cathode material at the other side, let's say a 4 volt material, you need to protect the thiophosphate by suitable films that are not electron conducting so that you avoid oxidation and reduction. So I think you will need, as with liquid electrolytes, proper interface design to really bring these electrolytes into the battery. Okay, so I think final part is then on fuel cells, and I think this is, of course, if you're interested in batteries, you always ask for properties of full solid-state cells. And as this is, of course, a wide field, I will concentrate only on 2 aspects. Of course, the lithium metal anode is one interesting aspect, but this is really something which is enough for another talk. I will concentrate really on the point that the cathode, in fact, will be a mixture, a composite of the active material, the storage phase, electron conducting path, and ion conducting path. And the question is, what is the ideal architecture for that? For these percolating composite, cathode composite. And the other thing is that, well, in liquid electrolyte, the volume expansion of the active materials during intercalating or deintercalating lithium do not play a major role because the liquid electrolyte is viscous and it takes up the volume changes. But if you have a ceramic electrolyte, you may end up in problems with the volume change of the active materials. The solid electrolyte may not follow that, and then you may get, of course, ruptures, all the mechanical problems. So the chemomechanics of solid-state batteries, I think, is an interesting issue. This is, of course, definitely a plus for polymers, because polymers, I think, are more, I would say, mechanically on the liquid side. They're quite plastic, so that's another point which I think would be good for polymers, but are definitely a deficit of inorganic materials. Now, this is 2 slides on the percolation. And Florian, who is a postdoc in the Bella Lab in Karlsruhe, he did a study on using 3 different, I would say, the same material. It's an NCM, so nickel, cobalt, manganese oxide, 60% nickel, 20% cobalt, and 20% manganese, typical NCM cathode material in this solid electrolyte at room temperature. And he tested it in a liquid LIB. You see, well, different depending on the size or independent of size. So these are particles where the majority of particles have a diameter of about 15 micron, 10 micron, and 5 micron. The performance is more or less the same. But if you put that into a solid-state battery, you see the smaller particles perform much better than the larger particles. And the reason is, in fact, that if you go to these large particles, and this is an XRD of just one reflection of the cathode material, and where, of course, the shift of the line is a measure of the degree of lithiation or delithiation. And after the first charge, you see that with the large particles, only 60%, only 70% of the large particles have been charged. The rest remained uncharged, seem not to be connected. And for the small particles, all the particles have been charged. And if we look for the partial conductivities of the cathode composite, we find that, in fact, the ionic transport across the cathode composite, so electrolyte plus cathode material, well, the ionic transport coefficient, the ionic conductivity is virtually the same, but the electronic percolation really differs very much. And that means, and this is simple, I think this is a very simple geometric argument. If you have a few big chunks in a matrix, same fraction of material, you easily lose a few particles. That makes a big difference. Now, the smaller particles, they seem to form a very efficient percolation network where virtually all of the particles are somehow being connected. So, and this is very important. You may consider that as trivial, but this is an important issue for a company selling cathode materials, because they had the idea to sell the same cathode material to companies producing solid-state batteries. But the point is, it looks as if you need specifically designed cathode materials for solid-state batteries. And this, of course, makes, I would say, quite a difference. Okay, final point is on chemomechanics. And Linda has to give me a sign if I run out of time, but I think still it's okay. So what you see here is, well, all the cells I will show you still are kind of button-type cells, so coin cells in principle, which are mechanically processed. So what we do is we simply take the materials and we mechanically put them together. So it's still not slurry-based. And this is, for example, then of course such a battery simply looks like a pellet. And with the X-ray tomography we use at Berlin, at the Helmholtz Center, we looked at the cells, and what you see that easily, that after charging, for example, a battery where it really deforms completely due to the chemomechanical expansion of the electrodes. What is also nice is that if you have a pristine solid electrolyte, which is in such a battery, and we will see that easily you can create pressure by charging, after that your solid electrolyte may really densify and you have less pores. So, which points out that you may have a kind of mechanical formation step with solid electrolytes if your materials deform properly. So I think this was just an initial experiment demonstrating that these chemomechanical expansion is important. So we thought we need more experiments to look deeper into that. So what we did, we created this kind of little, about that size, hot press, where we have a pressure sensor. We can expose pressure to a cell here. We can heat it, and we can measure all the electrochemical data. And that can be put into a glove box. So we have a small hot press in a glove box and can make pressure-controlled measurements of solid-state batteries. So this is the inside of the cell. So this is just essentially a coin cell under rather, I would say, complex boundary conditions. Okay, and then you can, I think we designed in principle 3 experiments. One is quite, I would say, trivial, but very important, and is not in this hot press, and that is just determining really the cell parameters for electrode materials as a function of degree of lithiation. So we need to know precisely the volume change of electrode materials to later calculate really the pressure changes in a battery. So this is just crystallography. But very important and interesting for most of the cathode materials. These data were not reported, I think, in a very detailed way a few years ago. And then we do 2 experiments. One is that which is, I think, just academic. We measure the voltage of a battery as a function of pressure. You will see, if you go to thermodynamics, you will see the change of the OCV of a battery as a function of pressure is given by the volume change, the volume change of the cell reaction divided by Faraday's constant. And I can tell you this will be, of course, on the microvolt scale, so not too much, up to millivolt. And the other thing which is more interesting is, of course, if you have a cell in a constant volume and you cycle your cell, what is the pressure being built up then? And this is, I think, quite the interesting point. Now, this is something, again, which has been done in the Bella lab. What we did is we collected data. So this is just, I would say, the integral information on the volume change, the relative volume change of different cathode materials as a function of delithiation. So this is the lithiated material, which would mean in the discharge state. And you see lithium cobalt oxide, this is LCO, lithium cobalt oxide is the only material which, upon delithiation, so you take lithium out, but the material expands. So why is it expanding? Because you remove the Coulomb glue between the layers. And then the negatively charged layers simply repulse each other and the volume expands. Or if you take out too much lithium, then the structure somehow seems to be partially collapse, and then, of course, you also shrink as it should be. Now, for the all nickel-containing materials, there is only continuous shrinkage. I would say slow shrinkage, and then if you pass the 60% delithiation, then it goes faster. And that is due to the fact that you go from nickel 2+ to nickel 4+. Nickel 4+ is really much smaller, so you overcompensate by the nickel 4+ formation the removal of the Coulomb glue between the layers. That's the simple result. And if you put that into a thermodynamic picture, we say this is the partial molar volume of lithium as a function of delithiation. You see, in fact, lithium cobalt is an exception. It's the only material that has, in the major part of its field of operation, a negative partial molar volume, which is quite an exception. All other materials will expand if you bring in lithium, as one would, I would say, intuitively expect. And in fact, you see lithium metal, which is always considered to be bad, because if you remove lithium, you create a hole. And the partial molar volume of lithium, of course, is nothing else than the molar volume of lithium. It's, of course, constant. And some of the nickel-containing materials really are worse. So they show a stronger volume change if you take out an atom of lithium than lithium metal itself. Now, this is the basis, of course, for making all these experiments. So let's ask first, what is the change in OCV as a function of pressure? And this is measured here. So you see this is really quite a lot. So this is a bar. So we go from 500 to about 2,000 bar. And the OCV changes, you see here, by about 10 to 20 millivolt. So this is nothing which is relevant for practice. So the pressure dependence of a battery is not too serious. But on the other hand, and that's what we did, that's a very nice work of Raimund again, who obtained his PhD, or will obtain his PhD hopefully in 2 weeks. What you see here is a battery, a solid-state battery out of lithium titanate, which is known as a zero-strain material. It doesn't change its volume very much, really below 1%. And lithium cobalt oxide. So what we know is, if we charge this cell, we take out lithium from lithium cobalt oxide, put into lithium titanate. So what will happen is that we take out lithium, and lithium cobalt oxide will expand. And in fact, you see it's charging of this battery, discharging, charging, discharging, and we charge, and the pressure is increased. So this is a pressure signal. Pressure increases, goes down, so reversibly, at higher C rate, we get less pressure change simply because the cell is not fully charged and discharged. And you can get something like the pressure hysteresis, and the pressure is not so much, it's just a change of 0.6 bar. I think that's not too serious. The same with NCM material, but exactly the other way around. All the nickel-containing materials shrink when you delithiate, and in fact, we charge and the pressure sinks. Discharging, pressure goes up, and it's the same order of magnitude, 0.6 bar. Exactly the other way around. Now, and even these small effects, this is just pictures of a electrode containing, of a composite containing NCM 811, so 80% nickel-containing NCM material. And you see, after 50 cycles, the material has, so to say, shrunk and expanded, and has sort of really opened up gaps to the solid electrolyte. And what is the result is, of course, that the capacity is fading due to really kind of mechanical, I would say, gap formation in the composite. Of course, you can compensate that by adding pressure, but I think in a real cell, real large-scale cell, you don't like to give too much pressure because you would need to use strong steel plates in your car to create that pressure. And this is definitely something you don't like to do. Okay, if you go to lithium, this, of course, becomes more serious now because lithium has quite a substantial volume change. And you see, again, we have this hysteresis, but the volume change is now 15 bar. The pressure change is 15 bar, but this is 15 bar just measured in one direction with our pressure sensor. And together with specialists from our mechanical department, they are specialists of continuum mechanics, we estimated that really something like the hydrodynamic pressure in that material is up to 600 bar, and the variation of 600 bar inside the cell. Now, Raimund had a nice idea, just in order to avoid that problem, simply to mix mechanically lithium cobalt oxide and NCM material. And in fact, you end up then with a mechanical blended material where the overall integral pressure change is, of course, not that big. So that could be one idea to mitigate these volume problems by mechanical blending. But even then, what you don't do is you don't avoid the volume changes at all. You simply have a very inhomogeneous, I would say, strain formation inside your composite. And that something we nicely showed together with Peter Bruce in the study. So in fact, it works. The contact between the cathode particles and the electrolyte is better. But in the case with lithium cobalt oxide, we could show that the lithium cobalt oxide particles locally really experienced strong stress, so that they really completely, I would say, due to shear strain, deformed. And that's also part, of course, of the loss of capacity. So I think, as with lithium titanate at the anode, we need to look for real, I would say, zero-strain cathode materials. And in fact, Toyota knew that already quite ahead. In 2014, they patented a reduced-strain cathode material for solid-state batteries. Interestingly, it's, I would say, quite an exotic material. Nobody would use it, but in principle, you can do that. You can create, by bringing together certain cations, you can create, like lithium titanate, a zero-strain cathode material. But this was only a theoretical study. Okay, finally, and I'm really very close to the end now, the question, what do our cells do? Well, again, I'm a physical chemist. I'm not an engineer, so I'm looking for model cases. And so what we did, said, okay, let's really look for lithium anode-containing cells with a reasonable cathode material, and let's use a reasonable solid electrolyte, see what we can get out with, I would say, not too much optimized cells. And the results are not too bad. So this is the capacity for 200 cycles. The Coulombic efficiency is really quite good. Well, there is fading, of course, because our NCA material is not coated, and our solid electrolyte is being oxidized at the cathode. That's a major part for that fading. So the next step is, of course, now coating the material properly, and that will surely improve. But the question is, what is the benchmark? What are the best solid-state batteries today being done? And this is from Simon, he is another PhD student, and Felix, who is a postdoc. They took all the reliably available data from the literature and put that into this Ragone chart. We see these brown triangles are from a recent paper from Toyota together with Kato. They published a high power cell with really thick electrodes. And you see, this is already 200 to 300 watt per kilogram, which is quite good. So they today show, I would say, the best performance with respect to high power. And these red data are from our group. These are Simon cells, unoptimized lithium metal NCM622 cells. Well, not high power, but I think energy density, we are better than Toyota. And then you may ask, oh, what's this? The blue stars. This is from a paper of Hong Li from China, where they used the conversion reaction of cobalt sulfide in a lithium thiophosphate electrolyte. But unfortunately, in this diagram, Simon took the data too uncritical, so he did not read properly. And in fact, he overlooked that these data only referred to the energy density if you only take the cathode material. So in reality, and I don't have an actual graph where these data now are much below, I think, the data by Kano and us. So I would say, for a short period of time, we may say we hold the world record in energy density, however, with a quite unpractical power density. So Toyota, of course, is, in that sense, quite ahead, but I think we have still not quite optimized cells. So this is our cell here, and Kato is here. He only has 40 cycles, and we, of course, have more cycles. And this is, again, as I said, has to be downgraded due to, I would say, a miscorrection of the energy density. Okay, with that, I would like to end saying that if you read in the news that solid-state batteries will very soon be commercialized and will drive cars, I think this is very optimistic. We are still in an early state, I would say, of development. I think there is promise that they can do quite well, but still some issues need to be solved, right? So processing, lithium metal anode, stability, the cathode coating. So there's a lot of very nice, I think, challenges to be overcome and lots of work to be done. Comparison of different cells is still difficult. I think in the lithium case, in the liquid electrolyte case, there's lots of data, really high precision data, and comparison is very, very, everybody's used to present exactly the set of data to compare cells. I think this field, you see, even the small number of papers is still in quite an infant state. And there is room for a lot of improvement. Yet no standard of reporting full cell data sets. So please, if you work on that, report full data sets so that one can easily compare cells. With that, I'd like to summarize. I think solid-state batteries require probably more careful interfaces than even liquid-based batteries. At least, I think in the liquid case, we learned how to make nice electrodes and to form nice SEIs. I think optimized cathode design is still required. Chemomechanics, I think, is I think the problem is identified, and the question is whether we can find proper solutions to run out of these, let's say, mechanical issues. And benchmarking, I would say, is still an open issue. I'd like to thank my university, the state of Hesse, which I think they support us quite well, BASF company for long-term support and very generous support, I must admit, and the federal ministry, of course, also. The Karlsruhe Institute of Technology. And finally, I'd like to very much emphasize the work by Wolfgang Seyer, who is an excellent solid-state chemist, and without his, I would say, knowledge on making materials, I think we would not have so nice combined work. Wenbo did very nice work, Raymond and Simon and Florian, very grateful to them. And finally, I'd like to point out there is a conference in November at Frankfurt Airport, which we organize. Linda will be one of the invited speakers on solid-state batteries. So if you're interested, you may just fly over to Frankfurt Airport. Thank you for your attention. Sorry for stressing time.
That's okay. That's great. Thank you very much for your lovely talk. Questions? Oh, Ivan's already got.
Oh yeah, thank you very much for your talk. I have a couple of questions. So what is the typical thickness of the ACI which is formed in between lithium metal and the solid-state electrolyte?
Yeah, so we still have not looked at that with a TEM, which of course the ultimate source of information because the materials are quite beam sensitive. We estimate from the conductivity of the material the SEI is being composed of, we estimate in the case of the 711, the thickness to be in the range of, let's say, up to 20 nanometers.
And is it...
in the case of LGPS, it's much thicker.
Yeah, but actually this is a thickness at the OCV conditions, but what happens on site?
Good point. We are looking into that because, of course, a current in both directions may, of course, have an influence on the SEI, may even lead to a lithium formation on the... So this is an information... Well, I have no quantitative information on that, but we look into that. Yeah.
Oh yeah, and I also have a general question just about the thickness of the solid-state electrolyte.
Mm-hmm.
What is the minimal thickness which is enough to actually prevent dendrite formation and suppress lithium dendrites? Like how thick the electrolyte should be?
I think I would put it in a different way. I think first of all, I think I never saw any piece of work so far that showed ultimate dendrite safety. Of course, the thickness goes directly into the electric field across the electrolyte. I think it's more the mechanical properties of the electrolyte that are decisive. Now, let me put it that way. In order to be competitive with lithium-ion batteries, you need to prepare separator films that are thinner than 10 micron. The thinner, the better. And what is then the critical thickness with respect to dendrites, I can't tell you. So far, I think I'm quite pessimistic saying that so far I know not a single material that under the conditions which are required are dendrite safe, independent of thickness.
Are these solid-state electrolytes grain boundary free, or will they eventually have some very tiny percentage of grain boundaries?
So the garnet, for example, they always are polycrystals. You have grain boundaries. And then the dendrites grew through the grain boundaries, as is well known. In the thiophosphate case, I think, of course, if you have the crystalline phases, you will have grain boundaries, and dendrites appear to grow through these. But even if you have a glass without grain boundaries, I think it's work by Yatmin Chang. They showed that also their dendrites grow into the material.
Oh, thanks. And sorry, I have two more questions. Does the pressure hysteresis depend on the cathode loading, or is it a constant issue?
Of course, yeah. Well, we did not check that, but it should. Mm-hmm. So the more active material, of course, the more volume change.
So like
total.
0.6 bars for something like a couple of milliampere hours per centimeter square, but if the loading is high.
Well, I don't know the loading, but it was 70 mass percent of cathode material.
So basically, the high is the loading, the high is the hysteresis.
Yeah.
And you mentioned that the pressure change of lithium metal was measured only in one direction. But what happens to the surface of lithium? Does it expand? Or?
You mean that the surface of lithium changes?
Like the surface
Yeah, well, yeah, I can't tell you because we have no way to look into the cell. And after the experiment, the lithium is so intimately, I would say, connected to the cell electrolyte. So if you try to remove it, we have not yet, don't have any information on the microstructure of lithium after, let's say, 50 or 100 cycles. We just got a FIB-SEM, a new one where we can make very fast tomographs. And one of the first things we will do is look for the lithium electrode microstructure. This is already something we have on the plan, but not yet done.
I have a related question. So you said that the chemical reaction between the electrode and the electrolyte is diffusion limited. So
If you have a covering film, yeah.
Oh, okay. So would you expect like a pressure effect because the increased pressure would limit diffusion further?
I think the point is effects of pressure onto diffusion are really not so strong. You need really very high pressure changes to see a change of the mobility of ions. Of course, you can imagine that a jumping ion has to squeeze right across a gate of atoms, and if you increase the pressure, usually mobility goes down. But these effects are rather small, and the pressures we use here, I think, are not high enough to cause mobility changes.
As you showed in one of those paper, the carbon additive is very harmful to solid state batteries. So, but to some extent, carbon is a very necessary inorganic additive. So, what do you think? What's your solution to this?
Yeah. So, Shishan, that refers to, I think, the one slide I showed to the instability of the cell electrolyte at the cathode. I said I go to high potential, the thiophosphates are simply being oxidized. Now, the point is, this cathode potential, any electronically conducting material in the cathode will have that potential. And you need typically carbon additives to have electron path. And Wenbo, in fact, another PhD student showed that even a small percentage of carbon additive will cause additional harm to your cathode. And that was, I think, Kiso Kang from Korea, I think, just recently showed this exactly the same result. No idea. I think whether there is, I think the question is there any cathode carbon material that does not transfer electrons to the electrolyte by whatever, say, protection mechanism or so? I think this is an interesting point. The electronic path and the percolation of electrons in the cathode, I would say, is an overlooked or not, or say underestimated factor.
Yeah, I mean, the point is if you have an insulating coating on your
Right.
cathode in your cam, then you're already limiting electron transport, which of course you have to have it, though, in order that you don't degrade.
Exactly.
So this is
I don't have an answer. We also try to find a solution. Yeah.
And do you see the influence of the pressure to, the side reaction caused by carbon additive?
No, we have not looked at that.
Thanks.
Herman had her hand up there. I'm just.
So thanks for the talk. You had a discussion on the particle size on percolation network, and you discussed PP and polyparticles. Do you investigate lower, the smaller size particles, and do you kind of?
Yeah. No, we did just the experiment with these particles, where the smallest size was 5 micron. Now, what I know is from a startup company who is already working on, let's say, pouch cell type solid state batteries. They use exactly that size of cathode material, about 5 micron. Yeah, 5 micron seems to be quite good, because if you go too small, of course, you will have more and more surface, and you run into more and more problems with the reaction with the electrolytes. So there seems to be an optimum. And if you would look to conference contributions, for example, in IMLB in Kyoto, already people think of using single crystalline material.
Speak loudly.
This is just my curiosity, but have you ever observed crack on cathode materials on cycling?
Yes. Yeah. I think I had a picture that was, of course, a cathode material from a liquid-based electrolyte, and it's well known and, well, easy to, I would say, understand. If you have volume changes for high nickel materials, let's say of 5, 6, maybe even 7%, then the cycling and the lithiation, delithiation, of course, does not go homogeneously. Then the materials, in fact, crack, and this cracking is part of the long-term degradation. In fact, we saw the same. I don't have a picture with solid-state batteries, of course, because this is independent of the electrolyte. This is a kind of inner problem, cathode material inherent problem. But it's worse in solid-state batteries because the solid electrolyte cannot flow into these gaps or these cracks. A liquid electrolyte can, of course, go into these cracks, and that may not be too bad. But in solid electrolytes, of course, these cracks are more severe.
So over the years, perovskite solar cells has changed from a dye-sensitized design to a solid-state design, mainly as a result of changing the liquid electrolyte to, I think, organic-based electrolyte, solid-state electrolyte. So I was just wondering, why can't you take that solid-state electrolyte and apply it to batteries?
Which electrolyte, in fact? You mean perovskites?
So in perovskites,
Yeah.
So the design.
So you're talking about the hybrid inorganic organic perovskite.
Ah, okay, yeah.
So initially it started off as a dye-sensitized design,
Yeah.
which started off, you put perovskite material onto mesoporous titanium dioxide, and it used a liquid electrolyte, but the liquid electrolyte actually degraded the perovskite crystal. So it was, a few years later that they moved from a liquid electrolyte to a solid-state electrolyte. So I'm just wondering, why can't you apply
What is the solid-state electrolyte?
I don't know.
I haven't really done too much research. Again, I'm sort of an organic chemist, but I was just wondering why you couldn't apply the same principles over here.
Well, first of all, I think there is work trying to develop hybrid materials, mix, let's say, polymer, inorganic material, or whatever. So far, I have never seen a superior material coming out of that, because the problem is if you create composites of a polymer electrolyte and a, let's say, inorganic material, you create many more interfaces, and the ions have then to move from a polymer solvent into a crystalline solvent. And these, let's say, ion transfer processes seem to be kinetically hindered. Whether they are hindered by bad interface formation, whatever, it's, I think, not known, but all the works I know for these hybrid materials, they never result in any superior material so far.
So this is just...
It's a line of research which is definitely being followed.
Right.
But nothing, I would say, so far, at least to my knowledge, nothing useful came out.
Right, so this is specifically talking about like the battery world, because in terms of solar cell efficiencies, the efficiencies increase from about 8% all the way to 16%.
Yeah. I don't know about the dimensions of the electrolyte, so it may all be a combination of the dimension and the current densities you draw. So I think I have not enough numbers in my head to really compare that. So it's an interesting suggestion to look at that, but I think the idea of going into hybrid materials, that is definitely being done, but has not resulted in any progress.
Okay, thank you.
Yes.
Is there any temperature change during the cycles which affect the volume change?
That's a good point. I think what we measure, we have not specifically looked into that. So I would not say that we have placed a thermocouple, let's say, in a battery to really follow that. But I think because so far the current densities we use, you see the maximum current charge rate or discharge rate was 0.1 C. So I think these current densities are not high enough, I would say, to increase the temperature, I would say, to a substantial amount. So yeah, I think they don't heat up. But that would, of course, be a. Of course, yeah. This is considered to be one of the advantages of solid-state batteries, of course, because the point is, if you look for a liquid electrolyte, always the temperature dependence on an Arrhenius diagram, you have these curved dependence, and the conductivity, particularly at low temperatures, goes down very much for liquid electrolytes, and for solid electrolytes. For recrystalline solid electrolytes, you have really just a straight line in the Arrhenius diagram, so you don't lose too much conductivity, you go down. And well, on the other hand, you don't add too much if you go up with the temperature for the excellent solid electrolytes. So I think operation at low temperatures can be one of the real advantages of solid electrolytes. Of course, also high temperature operation because they're relatively stable. So this, I think, is one of the potential advantages, the temperature range you can operate in. So that would also mean that the temperature being created by charging, discharging may harm solid-state battery less than a liquid-based battery. But this is only, I would say, a suggestion and hope no supported result.
Okay, so you showed the interface formation of LiPon where it forms Li3P and lithium nitride, which are known to be good ionic conductors. So in that regard, have you done any work on phosphonitrides?
Yes.
Would actually just form.
In fact, well, I must admit, we want it. So if you check our papers, we have a series of 3 or 4 papers with Wolfgang Schnick from Munich on lithium nitridophosphate. And these are really, I would say, chemically beautiful materials. The conductivity is, I would say, mediocre at maximum. So it's not that good. But of course, our idea also was great. If we have these materials, and if we decompose them with lithium, we get a mixture of lithium nitride and lithium phosphate. The problem is you can only make these materials, most of these materials, by high pressure synthesis. And we never got any reasonable film out of that. So we could not study that. But in fact, we did the XPS experiment and found, in fact, it decomposes into lithium nitride and phosphate. But we're not able to apply it in a cell. But your idea is perfectly right.
I also have one more question. I didn't listen to you properly, but regarding the loading of your material in your cells, which you showed at the benchmark.
Oh, I think the loading is, we try always to be at least close to, I would say, lithium ion battery loading. So it's definitely a few milliamp hours per square centimeter, maybe 2 up to 3 at maximum, I would say, currently. Yeah. Not, I would say, not really competitive yet, but I think the highest loading, of course, was shown by Toyota with these 600 micron thick cells.
Go ahead.
Oh, yeah. Comparing stability of lithium of LPS glass and LiGPS versus lithium metal, you mentioned that formation of electronically conductive phases on the surface decreases stability and increases the interface resistance. Is it because basically of the reactivity of lithium germanium alloys which are formed with LGPS, or?
Yeah, that's our idea, that if you have LGPS and if you let it react with lithium, you form, of course, lithium phosphide, lithium sulfide, and, well, lithium germanium alloy. And that is electron conducting. So that means you create a phase in your SEI, which is electron conducting, so you get a mixed conducting composite film, and that's why LGPS really, I would say, is being decomposed quite fast, and you get degradation films easily the thickness of a micron and more within short time.
The same phenomenon happened when, for example, a lithium silicon alloy faces the LPS glass or some other solid-state electrolyte.
Yeah, I think.
Estelle says it's a problem with silicon.
Yeah, I think. We also found that silicon is being reduced, and of course then you may form lithium silicides. They also have some electronic conductivity, I think, and so that will also be a problem. I think I read or I heard that the tin variant, that the tin materials seem to have kinetic stability, but I wonder about that because tin lithium alloys that form should also have the same problem as the germanium stuff. So I wonder, we didn't look for the tin material so far. Oh no, we looked, we had some measurements with Linda materials, I think. That was the different phase, yeah. So we didn't look into the tin materials yet. But I would expect that they also degrade fast. So our experience, the best electrolytes forming decent SEIs is really just pure lithium phosphorus sulfur phases. So the Li3PS4, the 711, so these are really all these glasses and agarodites. I think these are the best.
Yeah, but in your paper you mentioned that some intermediate phases of lithium and phosphorus like LiPe are formed which are also decent electronic conductor.
Yeah, that may be. But at the end, we found that as you saw, that the increase in resistance was acceptable, I would say.
Yeah, and Li3P is it thermodynamically stable?
Yeah.
With,
I think Li3P is a stable phase. And we got some Li3P, pure Li3P from Thomas Fessler, Munich. And we even did some transport measurements of that.
So Li3 and you can't go anywhere. It's like lithium nitride, it's stuck.
Yeah,
It's
right. Yeah.
stable.
But I don't recall the numbers.
So all this really says is that you have to have an interface between
Right.
any electrolyte and your metal, if
Yeah.
it's artificial or
Right. I would avoid any metal in your electrolyte at the anode.
I have a couple of questions. Well, how do people think of things? So why do you think that the conductivity of silver electrolytes has been matched by lithium? Do you think it's because the silver is more polarizable as a cation? It squeezes around? It's got d-electrons?
Yeah. Well, this is the typical argument, right? So I think I can only agree with that. But I have no, would say, theoretical. I would say more sound theoretical arguments for that. But I would say it's the combination of a soft environment and a soft cation. So things to seem. I think silver is unbeaten, right, with respect to
It is.
mobility. Yes.
So you would agree with that?
Copper is also not too bad,
Yeah, same thing, d-electrons.
but copper has the problem of easily being oxidized to copper
Yeah,
2+.
yeah,
Yeah.
just more fundamentals.
Yeah.
And why do you think there are so few materials with P2S7 groups that have been crystallized? I'm testing
No
to see
idea.
how much Wolfgang is interested
Yeah,
in
well-
incorporating.
Well, I think despite so many
have
years,
comments
well,
on this.
no, despite so many years of cooperation, I have not transformed even partially into an inorganic solid state chemist. So, in fact, I don't know. It may be. It's because the P2S74 minus N9, the ditetraeder, maybe it's so close to other species that that can form out of that, that it's sensitive and that its range of stability maybe.
Because in the corresponding oxides, there's tons of examples of P2O7 pyrophosphates. Zillions.
Yeah, I think the redox chemistry is too easily going on, so I think that's.
Do you think it
Yeah,
goes
I think
to
it's really the point that the energy landscape has so many nearby sinks that the material easily goes into another thermodynamic system.
Well, yeah. And in your last slide, your power density was an issue mostly because you're using LPS, right?
Yes. Yeah. Right. Exactly. This is I think the model system I showed you. This lithium Li3PS4 NCM622.
What kind of LP? Where did
It
you
was
get
it was the better Li3PS4 we got from BASF.
Okay.
And the point is, this of course it is in any sense an unoptimized cell. But we wanted to have a reference. We say, okay, what is achievable with a minimal set of materials in a, let's say, most simple cell? Now, if that already works reasonably, I would say, we see that, of course, we're spending more effort now on protecting lithium, having a better electrolyte with higher conductivity, and maybe coating the NCM. I think you should really get much better data.
Results.
Well, I think that, but Toyota, I think they were not superior with respect to energy density, by no means. And if you look,
They had the cells that were really good at energy density.
yeah,
but
right. The
power
problem is
density
you will
was
see they have a lot of electrolyte in there.
Yeah.
The
A lot.
volume fraction, so 70 volume percent of cathode material, that sounds a lot. 70 mass percent, but that transformed into 50 volume percent. So I think that's not too good, I think, yet. And I think they used 40 or 60 mass percent or something like that. So I think they had lower fraction of active material in their cells than we have. I know they have good results.
But you're right, they did do that at the expense of a lot of electric.
And we had the lithium anode.
Right. CY.
One quick question. So you mentioned that in electrochemical SEM, where the detachment of the active material from the solid state electrolyte. Now, would you, from an, I guess, from a fusion perspective, would you rather put another? Would you try to find a clever way, find another soft material to allow that detachment less, or would you rather to put another additive? For example, like another binder or other type of conductor that would kind of close the gap?
The answer is yes. We would consider that.
So, and
And we consider that, but I can't tell more. It's, of course, clear-cut that you have to go that way.
so like adding sort of a material.
You know, there was always the rumor, I think that was still when the first results from Toyota were published, that I think I got some rumors from colleagues from industry say, well, you see, the solid-state batteries from Toyota are not so solid.
Okay. Well, but that's rumor.
So it may well be that you add at the end a bit of some miraculous liquid to make it a hybrid cell.
Just a little bit.
Yeah, just a little bit. You know, in chemistry, always a drop of water helps at the end. Often.
So we have the pleasure of having Professor Janek here, as I said, tomorrow and Friday and Monday, and he's in his office as QNC 3609. So if any of you want to
Oh, well, I would be happy to have a chat.
then in fact, I'm going to arrange formal meetings with my group, but anyone else is welcome to go find him. And you have to go to chemical engineering right now with your little piece of paper.
Okay.
And so let's thank Professor Janek again for his